Welcome to month 3 of the Data Engineer track. Today you are going to build a complete open source data platform from scratch, a lakehouse, and a data warehouse running side by side with dashboards on top. The stack you are building mirrors production architecture: Apache Spark for distributed compute, Delta Lake for reliable lakehouse storage, PostgreSQL for your structured warehouse, MinIO for S3 compatible object storage, Apache Airflow for orchestration, and Apache Superset for visualization on Azure. This maps directly to Synapse Spark pools, ADLS Gen 2, Azure SQL, Data Factory, and Power BI. Every skill you build today transfers to the cloud. Here is what we are covering today. 4 hours heavily weighted toward hands-on work. The first hour covers the concepts you need: platform architecture, the Medallion pattern, Delta Lake fundamentals, and data loading patterns. Hours 2 and 3 are dedicated challenge time, where you build everything. Hour 4 is review, performance comparison, and retrospective. We will produce 5 deliverables: a working Docker environment with all 6 services, Delta Lake Medallion cables across bronze, silver, and gold layers, a PostgreSQL star schema loaded from the gold layer, a superset dashboard with charts from both data sources, and a short architecture report comparing lakehouse and warehouse performance. The Azure parallel is worth internalizing early. MinIO is your local ADLS Gen 2. Spark is your Synapse Spark pool. PostgreSQL is your Azure SQL or Synapse SQL pool. Every skill you build today works in the cloud tomorrow. 5 clear objectives for today. First, you will deploy a multi-service data platform using Docker Compose. Standing up infrastructure and verifying connectivity between services is fundamental data engineering work. Second, you will implement the Medallion architecture, bronze, silver, and gold layers on MinIO using PySpark and Delta Lake. This is the dominant pattern in modern lakehouse design, and Databricks and Microsoft both standardize on it. Third, you will design a star schema and load it from the lakehouse into PostgreSQL. This bridges the two worlds: flexible lakehouse processing and structured warehouse serving. Fourth, you will build analytical dashboards in Superset, connecting to both Spark SQL and PostgreSQL to compare the experience. And fifth, you will benchmark Spark SQL against PostgreSQL with identical queries and articulate when each engine excels. This is the full picture of what you are building. 6 services across 3 layers. At the bottom is Apache Airflow, your orchestration layer. In production on Azure, this would be Data Factory. Airflow manages the DAGs that move data from raw ingestion through transformation to the final serving layer. In the middle, 3 systems work together. Apache Spark with PySpark is your compute engine. It reads, transforms, and writes data. Delta Lake on MinIO is your lakehouse storage. S3 compatible object storage with ACH transactions built on top. PostgreSQL is your structured warehouse. The star schema that serves low latency business intelligence queries. On top, Apache Superset and Jupyter Notebook handle visualization and exploration. Superset connects to both Spark SQL and PostgreSQL, so you can compare query performance side by side. The data flow is straightforward. Raw files land in MinIO. Spark reads and transforms them through the Medallion layers. Gold layer data gets loaded into PostgreSQL, and Superset queries both engines for dashboards. The Medallion architecture is the single most important pattern in lakehouse design. 3 layers, each adding data quality. Bronze is the raw ingestion layer. Data arrives exactly as it came from the source. CSV files, JSON payloads, whatever the format. You write it to Delta format, but do not clean or transform it. This preserves the full audit trail and lets you reprocess if upstream schemas change. On MinIO, bronze lives at a path like S3A, lakehouse bronze. Silver is the cleaned and conformed layer. Here you deduplicate records, cast data types correctly, handle null values, and apply business validation rules. Silver tables have enforced schemas. Delta Lake will reject writes that do not match the expected structure. Gold is the business-ready layer. Aggregations, joins, enrichments, core tables look like what a business analyst expects. Dimension and fact tables ready for dashboards and reports. This layer also feeds the PostgreSQL warehouse. The critical insight is that each layer is independently queryable. Data scientists might work against silver tables for exploration. Business analysts query gold for reports. Everyone accesses the quality level they need. On Azure, these would be containers in ADLS Gen 2 following the same bronze, silver, gold naming convention. Delta Lake solves the reliability problems that plagued data lakes for years. 4 core features matter for today's work. AC transactions ensure that when your Spark job writes to a Delta table, the operation is atomic. Other readers see either the old version or the complete new version, never a partial write. This eliminates an entire class of pipeline bugs that made traditional data lakes unreliable. Schema enforcement prevents bad data from entering your tables. If you try to write a data frame with a different schema to an existing Delta table, it fails immediately. Schema evolution lets you safely add new columns when your data model grows. Time travel is invaluable for debugging and auditing. Every write creates a new version of the table. You can query any historical version by timestamp or version number. The code on the slide shows how to read version 3 of a table. Just add the version as an option. On Azure with ADLS Gen 2, time travel works exactly the same way. Unified batch and streaming means the same Delta table serves both batch reads and Spark structured streaming. One table, 2 access patterns, no duplication. On the practical side, merge operations give you upserts for change data capture. Optimize compact small files for better query performance. Backup cleans up old versions to reclaim storage while preserving your retention window. 3 loading patterns, each serving a different purpose in the pipeline. Jupyter with PySpark is your interactive pattern. You use it for exploration and prototyping. Read a CSV file, inspect the schema, try some transformations, and write to Delta Lake tables. This is the primary tool you will use during the challenge. On Azure, the equivalent is Synapse Notebooks or Azure Databricks Notebooks. Airflow DAGs represent your orchestrated pattern. In production, pipelines do not run manually. You define directed acyclic graphs that schedule and manage the bronze to silver to gold flow with built-in retries, alerting, and SLA monitoring. On Azure, this maps to Data Factory pipelines or Synapse pipeline activities. PostgreSQL copy is your warehouse loading pattern. Once cold data tables are ready, you bulk load them into the star schema. You can use PySpark's JDBC writer, which handles type mapping automatically, or PostgreSQL's native copy command for maximum throughput. On Azure, the equivalent is Synapse copy into or Polybase external tables. During the challenge, you will primarily use the Jupyter pattern for building the Lakehouse and the PySpark JDBC pattern for loading the warehouse. This is the central question of today's session. When should you use the Lakehouse and when should you use the warehouse? You will answer this with real data during the challenge, but here is the framework. The comparison tells a clear story. Spark excels at scale. Petabyte range distributed processing with cheap object storage underneath. PostgreSQL excels at speed for structured queries, millisecond index lookups, high concurrency with connection pooling, and sub-second dashboard responses. Data format is a key differentiator. Delta Lake uses open Parquet files, no vendor lock-in, readable by any engine. PostgreSQL uses its own internal page format, optimized for its query engine, but proprietary. For machine learning, the Lakehouse wins hands down. Spark Semlib and Python UDF support mean data scientists can train models directly on Lakehouse data. PostgreSQL requires extracting data to a separate ML environment. Cost is another clear advantage for the Lakehouse. Object storage on MinIO or ADLS Gen 2 is dramatically cheaper per terabyte than database storage. The bottom line, use the Lakehouse for large-scale ETL, data science workloads, semi-structured data, and cost-sensitive historical storage. Use the warehouse for low-latency BI dashboards, high-concurrency query workloads, and strict relational governance. In most production systems, you use both, and that is exactly what you are building today. Now for the hands-on work. 4 parts, building incrementally toward a complete platform. Part 1 is environment setup, budgeted at 30 minutes. You will get a Docker Compose file defining all 6 services. Your job is to bring everything up, verify that each service is running, and confirm you can access the web UIs. This sounds straightforward, but networking issues between containers are the most common blocker. Taking time here to get it right saves frustration later. Part 2 is Lakehouse data loading, budgeted at 45 minutes. This is the core of the challenge. You will load raw CSV files into bronze delta tables, clean them into silver tables, and aggregate them into gold. By the end, your gold layer should contain dim customer, dim product, and fact sales tables. Part 3 is the star schema, budgeted at 30 minutes. Design your dimension and fact tables in PostgreSQL. Load gold data using PySpark's JDBC writer, and write at least 3 analytical queries that join facts and dimensions. Part 4 is dashboards, budgeted at 15 minutes. Connect Superset to both PostgreSQL and Spark SQL. Build 3 charts and assemble them into one unified dashboard. The scenario: you are the data engineer for a retail analytics team. Management needs unified reporting from sales, inventory, and customer data, serving both data scientists on the Lakehouse and business analysts on the warehouse. Let us walk through the first 2 parts in detail. Part 1 covers Docker setup. The compose file defines containers for Spark master and worker, MinIO, PostgreSQL, Airflow, Superset, and Jupyter. After running Docker compose up, verify each endpoint: Spark UI on port 880, MinIO console on 9001, Airflow on 881, Superset on 888, and Jupyter on 8888. A common gotcha: MinIO needs buckets created manually before Spark can write to them. Use the MinIO console or the make command line tool to create the raw and Lakehouse buckets. Part 2 is where the real data engineering begins. Start in Jupyter with PySpark. The bronze loading pattern is straightforward. Red CSV with info schema enabled, write as delta format to MinIO. For silver, add cleaning steps, drop duplicates, filter out null values, cast data types correctly. For gold, join and aggregate your clean tables into dimension and fact structures. Notice the S3A protocol in the code. That is how Spark communicates with S3 compatible storage like MinIO. The same protocol works with Azure Blob Storage when configured with the ABFS driver. Schema enforcement is your safety net throughout this process. Once you write the bronze table, Delta records the schema. If your silver transformation produces incompatible types, Delta catches it immediately rather than letting bad data propagate downstream. Part 3 tackles the star schema in PostgreSQL. The diagram at the bottom of the slide shows the target. Dim customer, dim product, dim date surrounding the central fact sales table with foreign key relationships. This is a classic Kimbo star schema. 2 loading approaches work well. PySpark's JDBC writer is the cleanest. Read the gold delta table into a data frame and write directly to PostgreSQL. Driver handles type mapping automatically. Alternatively, you can export gold data to CSV and use PostgreSQL's copy command for maximum throughput. The PySpark approach is recommended for the challenge because it maintains the code-first workflow. Write at least 3 analytical queries that demonstrate the star schema's value. Examples include total sales by customer segment, monthly revenue trends over time, and top-selling products by category. Each query should join the fact table with 1 or more dimensions. That is the fundamental value proposition of the star schema design. Part 4 brings everything together visually with Superset dashboards. Connect Superset to PostgreSQL using the SQL Alchemy connection string and to Spark SQL using the Hive server connection. Build at least 3 charts: a bar chart, a line chart, and a KPI indicator. Combine them into one dashboard that tells a cohesive analytical story. The most interesting exercise is running the same query on both backends and comparing response times in the dashboard. You will see PostgreSQL win on small index queries, while Spark SQL performs comparably or better on full table scans over larger datasets. Now let us look at the performance characteristics you likely observed during the challenge. The benchmark numbers on the slide are representative. Your specific numbers will vary based on data volume and container resources, but the pattern is consistent. Spark SQL has startup overhead. A simple select on 10,000 rows takes about 2 seconds because Spark needs to plan the query, schedule tasks, and coordinate execution across its distributed architecture. PostgreSQL returns the same query in roughly 50 milliseconds because it is already warmed up with in-memory indexes, where Spark shines is at scale. At 1 million rows, Spark's distributed processing starts to close the gap on aggregations. At 10 million rows, it is clearly faster on full table scans because it parallelizes reads across partitions and executors. PostgreSQL wins decisively on concurrent queries. 10 simultaneous queries average under 2 seconds each, while Spark struggles with session contention and resource scheduling overhead. For Delta Lake best practices, partition your tables by date for time series queries, run optimize regularly to compact small files, and use that order on your most frequently filtered columns, and configure vacuum with a sensible retention window. 7 days is a good default. For PostgreSQL best practices, create indexes on all foreign key columns and frequently filtered columns. Run analyze after every bulk load to update the query planner statistics and avoid select star on fact tables. Always project only the columns you actually need. In this final hour, we review what you built and reflect on the experience. Start with the architecture review. Trace one record end to end. A raw CSV row enters the bronze layer as is, gets cleaned and validated in silver, gets aggregated into a star schema structure in gold, gets loaded into PostgreSQL, and finally appears as a data point in a superset dashboard chart. That is the complete data lifecycle, from raw ingestion to business insight in one session. Compare your Spark SQL and PostgreSQL query results side by side. Same query, same data, different engines, different performance profiles. This hands-on comparison is more valuable than any theoretical discussion. The answer to should we use a lakehouse or a warehouse is almost always both for different workloads. Check schema consistency between your Go Delta tables and your PostgreSQL DDL. Are the data types aligned? Are nullable columns handled the same way? Schema drift between the lakehouse and warehouse is one of the most common production issues in dual serving architectures. For production readiness, consider what would change. MinIO becomes ADLS Gen 2 or Azure Blob Storage. Spark becomes Azure Synapse Spark Pools or Azure Databricks. PostgreSQL becomes Azure SQL Database or Synapse Dedicated SQL Pools. You add monitoring with Azure Monitor, alerting with PagerDuty or Opsgenie, security with Azure Active Directory and service principals, and governance with Microsoft Purview or Unity Catalog. The retrospective asks 3 questions. What went well? What was the smoothest part of the build? What was tricky? Where did you get stuck or spend more time than expected? And what would you change? Different tool choices, a different schema design, a different approach to any part of the challenge? 5 deliverables, weighted by complexity and data engineering significance. The Docker environment is worth 15%. It is foundational infrastructure, but the tooling does most of the heavy lifting. The Delta Lake Medallion tables carry the highest weight at 30%. This is where the core data engineering skill lives, designing the transformation logic, implementing schema enforcement, and building the bronze to silver to gold pipeline. The PostgreSQL star schema is worth 25%. This covers schema design, data loading from the lakehouse, and writing meaningful analytical queries that demonstrate the star schema's value. The Superset dashboard is worth 15%. It provides visual proof that your entire pipeline works end-to-end. The architecture report is worth the final 15%. This is your written reflection covering performance comparison results, architecture decisions you made, and recommendations for moving this platform to production. Scoring ranges from distinction at 90 and above, which requires all 5 deliverables plus bonus work, down through merit at 70 to 89 for all core deliverables, pass at 50 to 69 for at least 3 deliverables, and retry below 50. That wraps month 3. Today you built a complete data platform from scratch, a lakehouse and a warehouse, running side by side with dashboards serving real queries from both engines. The big takeaway is that lakehouses and warehouses are not competing technologies. They are complementary. The Lakehouse handles scale, flexibility, and cost-efficient storage. The warehouse handles speed, concurrency, and structured governance. Production systems use both, and now you have hands-on experience building and comparing them. Next month, we go deeper on orchestration and monitoring, advanced airflow patterns, data quality frameworks, observability pipelines, and alerting strategies. If today was about building the platform, next month is about keeping it running reliably in production.